Hello friends, welcome back my video lecture. In this video lecture, we have to see the classification of ion exchangers. Okay, we can separate the particular component from the mixture by using the ion exchanger, or we can say resins. Okay, they having the high molecular weight. Okay, they can classified into two types. In the first one is cation exchanger, and the second one is anion exchanger. In the cation exchanger, we can see that they exchange the cations. So, for example, you can take SO3H minus, okay, and COOH, and you can see minus OH minus SH, okay, and this kind of minus PO3H2. So this cation exchanger we can use for the uh, as a ion exchanger. Okay, and the next anion exchanger, in this case they exchange the anions. Okay, they exchange the anions. You can see here NH2 and NH here, and R you can take here, and NR2 and NR plus 3. So this kind of ion exchanger we can use in the cation exchanger and anion exchanger. Now we have to see the action of ion exchange resins, how ions exchangers are working, or how resins are working into the case. Okay, so first of all we have to see the cation exchange region in, and the next one is the anion exchange region, cation exchange region and anion exchange regions. So we can take the first one is this reaction like this: RH and plus some any one metal will be there, so it will dissociate. So RH will be dissociate, and there will be the form Rm, so that M will replace H. Okay, and here H plus will form. So Rm, this is one of the product, and the H plus will be displaced by the metal. Okay, and see here cation exchanger. Here the cation exchange strong acid resins will be there. Okay, the next one is the weak acid cation exchanger into the strong acid and resid and weak acid resin. In the strong acid resin, they are highly insoluble. Strong acid resins are highly insoluble. Okay, highly insoluble. In case of water, you can consider. Okay, and the pH range of this strong acid resin will be 1 to 14. This is the pH range of that um, cation exchangers. Okay, and for example, you can take here Dovex 50, Amber Light IR 120, and Dow Lights C20. So these examples we can see into the strong acid resins. We should know the pH range, and they are insoluble into the water. Right, now we have to see the weak acid resins. So they are partially insoluble. Okay, they are not completely soluble into the water, and the pH range will be the 5 to 14. Okay, 5 to 14. And in this case, for the weak acid resins, we can take examples: Amber Light IRC50 and Permetit H70 and Herexin 120. So this example we can use as a weak acid resins. Now next is we can see this reaction here: RNH3 plus OH minus ions and A minus. Okay, and here they will attract, they will form like these compounds RNH3, okay, A minus and OH minus. This way it will form, and this is the anion exchangers. Again, in this case you will see the strong base resins and the weak base resins. Okay, anion exchangers, strong base resins and weak base resins. So in the strong base resins, you can see here they are highly insoluble. Okay, they are highly insoluble strong base resins, and the pH range is 1 to 12. Okay, pH range is 1 to 12 of these kind of resins. And for example, you can see here the Dovex 1 amber light IRA foot 100 and the permitted S1. So this example we can see in the strong base resins. The next is weak base resins. They are partially insoluble. Okay, these are also partially insoluble. The pH range is 5 to 14. And the examples you will see the Dovex 3 amber light IRC 45 and permitted W. So these examples we can take as a weak base resins. Okay, and now we have to see the types of ions exchange resins. Ion exchange types. You will see table here. Types exchanges are given. Their functional exchanges groups are also given, and trade names. Their trade names are given. So first of all, you can see here the cations and here anions. Okay, and their groups and the trade names. We can see a one okay, from the cations and anions. The strong acid you will take as a cations, strong acid, and sulfonic acid SO3 H. This is the functional group. Okay, exchanger group, and their names are Dovex 50 and light IR20. We have seen there, okay, in the cation exchanger. Okay, and for the weak acid, carboxylic acid. Okay, this is functional group, and the example is amber light IRC50 and resin 102 permitted H70. And for the anion exchanger, okay, we can see for the strong base quaternary ammonia ions. Okay, this is the functional group, and CS3 thrice group plus Cl minus. Okay, an example is OX1 amber light IR A 400 and arene hexene 201 and permitted TS1. And for the weak base amine groups NH3Cl, right, the Dobex 3 trade names Amberlite IR45 and Rexin 203 permitted W. So all these trade names for the weak bases functional groups is amines, right? So these are the types of ions exchange reagents. Now we have to see the ion exchange capacity of commonly used resins. Commonly used resins. So some resins are given here. They are commonly using for the separation of ion exchange. Okay, and their capacity we have to see diorite C225 in a plus form. So the capacity of this resin is 4.5 to 5. Okay, this is the ion exchange capacity moles per gram of resins. And zeolite 226 H plus form 9 to 10. This is capacity. And diolites A 113 Cl minus form. This is the 4 capacity, and amberlite IR 45. This is the 5 capacity. So this kind of capacity we should know for the using of resins. Now we have to see the applications of ion exchange chromatography. In this case, where we can use ion exchange chromatography, which kind of mixture, which kind of component we can separate from the mixture. Okay, so here we can use this technique, the separation of metal ions and non-metal ions on an anion exchange resin column. So if you want to separate the metal ions and non-metal ions, so which can this kind of technique we can use here for the separation of ions. Okay, the next is the purification of water. If you want to purify the water, then we can use this kind of technique, ion exchange chromatography, for the separation of water. Okay, so these two applications are given for the ion exchange chromatography. Now we have to see the next, this is the size exclusion chromatography. So this is the depends on the size of the particular component. Okay, we can separate each other from the mixture. Okay, so in this case the separation of large molecular mass species only. So in this separation technique, if you want to separate only larger molecule mass of species, okay, we can see like a resins. Okay, and the next one is the porous material solid silica particle size is, we are using porous material silica, solid silica. Okay, and that particle size is 5 to 10 mm. Okay, this is the size of that silica particle size. The next is dextran, agarose, or polyacrylamide are commonly used polymer as packing material. Okay, So in this system we can use this kind of materials, this kind of component for the packing material. Okay, polymer as a packing material. The next is the separation of molecules range from molecular weight. Okay, this is the limitation of this technique. Okay, size exclusion chromatography, this is the limit. Separation of molecules only range from molecular weight of 1000 to several millions only. Okay, this is the limitation. So between this range we can separate the molecules, okay, by using the size exclusion chromatography technique. Now where we can use this kind of technique, that means the application of the size exclusion chromatography. In the first one is, it is mainly used for the separation of protein. If you want to separate the protein from the particular mixture, then we can use the size exclusion chromatography, the proteins having the high molecular weight. Okay, so this kind of component we can separate by this technique. Next is, it is also used to obtain the molecular weight distribution of polymer. Okay, so if you want to distribute the molecular weight of polymer, then we can use this technique. Next is, it is used in the separation of enzymes, peptide, nucleic acid, hormones, and polysaccharides. Okay, so this kind of component also we can separate by this technique. And next is, it is used to examine the stability of characteristics and the natural organic matter in water. So if you want to analyze this kind of things, okay, about the natural organic matter in water, so this technique we can use for the analysis of this kind of things of water.